So in the previous video, we looked at solving recurrence relations and not to non-homogeneous recurrence relations. I gave you this table here of particular solutions that you might want to try to find the general solution to these non-homogeneous recurrence relations. And I said in the last video that there are some special cases where this doesn't work. So in this video, we want to consider the times when actually it doesn't work, and in this table, what the particular solution given in this table tells us is not the particular solution we need to consider. So I'm going to use the same recurrence relations as before. So I'm going to take the recurrence relation here that we used before, but in this case we're going to consider when f of n is equal to 2 times 5 to the n. Okay, and normally you'd want to consider a particular solution here of a times 5 to the n. But the problem here is that we notice that the form of f of n, 5 to the n, is also included as one of the two parts of the solution to our homogeneous recurrence relation. So this isn't going to add anything else to our solution because it's already in the h of n part. So what we need to do in this situation, and for reasons I'm not going to explain why, we're going to multiply this by an n. So in this case, because there is already a 5 to the n in h of n, the particular solution needs to be multiplied through by a factor of n. So a similar situation which that would happen if we had f of n were equal to 3. Well, 3 is a constant, right? 3 is a constant, and we can see that h of n also has a constant term b. So what we can't do is we can't just use what our table tells us and to consider some constant a, because that's already been included there in this b here. We need to multiply this a by an n. Well, what other f of n's could we consider? Well, let's consider f of n being linear. So let's say f of n is equal to 8n. Well, if f of n is equal to 8n, it may look like that there isn't any linear terms in here. But really what we're interested in is the fact that this is polynomial. So the fact that this is polynomial here means that there kind of is a polynomial part to h of n. So again, your normal p of n would be an plus b, but we need to multiply this through by n, and we will get an squared plus bn here. And you could have a plus c, but you don't need a plus c because that plus c will be absorbed into the value of b in h of n. Finally, we could consider when f of n is something quadratic, and the same thing is going to happen because hn has a polynomial part. Then if f of n is 24n squared, we can't just consider pn as being a quadratic. We would need to multiply that quadratic through by n. So if we had p of n, your normal table above would tell you should consider that as being an squared plus bn plus c. But we need to multiply that through by n because f of n is polynomial and h of n has a polynomial part. Okay, let's have a look at the next recurrence relation. So the next recurrence relation was this one here, and I told you that this had a general, the homogeneous relation had a solution here. Well, what could cause us problems here? Well, if our function f of n has a 2 to the n in it, or it has a 7 to the n in it, then we need to again do something different. So let's consider when f of n equals, 3 times 2 to the n. Well, this has a 2 to the n in it, and there's a 2 to the n in it here. So the particular solution we need to consider, rather than just being a times 2 to the n. We need to multiply this through by n. So we get a n p to the n. Well, what other things could cause us problems? Well, a 7 to the n would do as well. So if f of n were, say, 7 to the n minus 3n, well, here, this part is not a problem because there is no polynomial term in Hn. So here, this part will follow our ordinary pattern from the table above. But this part is a problem because there is a 7 to the n in our h of n. So the particular solution we consider here is going to be a times n 7 to the n plus a linear term bn plus c. Okay, well, the next relationship we had was this one here, and we had the general solution here to the homogeneous relationship. So what fn's will cause us problems here? Well, anything with a minus 5 to the n is going to cause us problems, and also anything with an n minus 5 to the n is going to cause us problems. So let's consider some things that can happen here. If we had f of n being, I don't know, let's say 2 to the n plus 3, well, that is no problem at all because there is no 2 to the n terms here and there is no polynomial terms. So this would just be our a 2 to the n plus some constant here. But if we had f of n was, say, 3 times minus 5 to the n, then because there is a minus 5 to the n term in f of n, and because that also appears in our h of n, we need to multiply the particular solution through by n. So we would actually get the a minus 5 to the n, but we need to multiply that through by n. But notice here, when we multiply this through by n, the n minus 5 to the n term is still in our h of n. So this is going to be no good as well. So actually now we need to multiply this through by n again. So the particular solution we need to consider here is Pn equals an squared times by minus 5 to the n. Finally, one more to consider is if we have the recurrence relation un equals 2un minus 1 minus un minus 2 plus f of n. And the solution to the homogeneous equation here is h of n is linear. So h of n is equal to a plus bn, where a and b depend on the first and second terms of this sequence. Then if we think about different f's of n, if f of n is, say, 3, well, our table would tell us we have to consider p of n as being some constant a, but because there is a constant in h of n, we need to multiply that through by n, but actually there is still a linear term in h of n, there is a bn term, so we need to multiply that through by n again. So we get an a n squared. You could, if you really wanted, have a plus a bn plus c here, but they wouldn't matter because they're already covered in the h of n. So we don't need that bn plus c. Similarly, if I had f of n equals 5n, well, we notice that there is a linear term of the same order here. So rather than considering our normal particular solution of an plus b, we do need to multiply that through by n, and if we expand that out, we get a particular solution of an squared plus bn. And again, you could have a plus c, but you don't really need it because that is going to be in this a term here.